All right, let's go and get started. So this is actually our last lecture of content for the semester. Assuming we get through everything that we need to get through today, my thought is we lecture today. I don't have class per se on Wednesday to give you time to work on your homework, and then you turn your homework in on Friday and we have the exam review, okay? So is everybody okay with that? But we do have some stuff to get through today in order for that to work. So got to have everybody on point for our last lecture. So the homework 9 is due on Friday. I have a copy of homework 9 up here in case anybody didn't get it. It's also on Blackboard, so I think everybody knows the drill there. On the 28th, on Friday, you turn in your homework. I give you back a copy of the solution. So, you know, no late homework is accepted for homework 9, okay? So I want everybody clear on that. On Friday, we'll review the solution, review what's on the exam. Any questions? That's what Friday's about. And again, assuming everything goes well, class is canceled on Wednesday. Everybody good? Okay. One final point. I still haven't gotten much of a response on this. I know it's not due till Friday, so I'm sure a lot of you are putting it off to the last minute. But please don't forget, it really does matter, at least to me. If you have any comments or things you'd like to see addressed in future semesters, it really does matter to me. And it's free points, so, you know, really no reason not to do it. Okay, so before we get back into our final example, or what is essentially our final example, I want to briefly go through the solution for homework 8. If you just came in, I was handing out homework 8s earlier. I can hand yours out after class, so if you don't have yours, don't worry. Just come see me after class. I still got a pile up there. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. There's that. And then there's that. Okay. So on this particular homework assignment, you had, I think it was a pretty straightforward assignment. The one thing that probably gave everybody some hiccups was either A, the algebra on problem 2, or some of the load distribution stuff on problem 3. So let me go through problem 1 first. I think problem 1, it was a little bit of a trick question, but if you look, the area of the flange was 11.25 square inches, and the area of this stem was 11.25 square inches. So where's the plastic neutral axis? It's right there. Okay, right where the 2 points meet. So literally just some moments about that point, you should have gotten a ZX of about 90.7 cubic inches. And that's about it. On problem 2, let me show you what I did for problem 2. So first off, for the moment, you know, it's literally just, you know, each point load times its distance from the support. So you should have got a factored moment of 595.2 foot kips. Keep in mind your moment needs to be factored. For deflections, though, you do not apply load factors. Now, this is how I did it. Let me show you something. Okay, so watch this. All right, I think this makes the algebra a little easier, so I want everybody to pay attention to this. So this is the deflection for the first live load, the one that's not on the very end, the one that's, let me see, the live load, the 16 kips. This is the formula for the deflection for the 16 kips. Now, it's a bunch of junk, but it's a function of Ix, and you're trying to solve for Ix. So watch this. So if I factor out Ix, I get this pile of junk times 1 over Ix. Is everybody okay with that? So if I calculate just all of this, I get about 961, and that's inches to the 5th, because if you divide that by a moment of inertia, that's where your inches comes into play. For case 22, for that point load deflection at the end, that's where I get PL over 3EI, and I get this. So if I add these two up, it's essentially just this over Ix plus that over Ix. So add those two up, and your maximum deflection has to be less than or equal to that over Ix. Just solve for Ix, and you get about 5,900, 5,887. I think that's a lot easier. It's a lot less algebra. So when you go into member selection, You have to select a member that has a maximum moment capacity of 595 foot kips and a moment of inertia of 5887. Now, if you select based off the ZX charts, you can select a 21 by 68, and it has enough moment capacity, but it doesn't have a required or enough of a required moment of inertia. So you go to table 3.3, pick the first section that works, which is the W33 by 118, then go back and check its capacity, and you've got more than enough. So your answer should have been a W33 by 118. As for problem 3, okay, so here's the problem. Now, unit weight of concrete is 150 pounds per cubic foot, or 0.15 kips per cubic foot. So let's take a look at the structural analysis. So first up, we've got the assumed beam self-weight of 100 pounds per foot. Now, the area, I think we've discussed this in concrete design, and I know for those of you that haven't had concrete design in a while, you have done this. To determine the self-weight of that slab, you take the unit weight times the area, okay? So what's the area of the slab? Well, it's the thickness times the tributary width. The tributary width is 8 feet. So 8 feet times 5 inches, you should have gotten 3.33 square feet. So gamma times the area will give you a dead load. So the slab weighs 500 pounds per foot. The beam weighs 100 pounds per foot. So 1.2 dead plus 1.6 live, you should have got a factored load of about 1.68 kips per foot. Again, for your live load, just take the pressure load times the tributary width. So your moment should have been WL squared over 8. That was 189 foot kips. So selecting a section, you should have gotten W16 by 31. It has adequate strength, and if you go back and update the load estimate, because this beam is lighter, you still don't get economy. If you remember, on one of the examples we did in class, we assumed a beam self-weight that was heavier. So we went back and updated the moments, and we found that we could actually pick a smaller section. That isn't the case here. It ends up still being the 16 by 31. So the 16 by 31 is your answer. Anybody have any questions on that? Yes. Yes. However you get that, whatever you feel comfortable with. I mean, there's probably 7 or 8 different ways of doing that problem that are all correct. It's really more about what you're most comfortable with. Some of you are going to be more comfortable just hitting solve on your calculators. Some of you aren't. I recommend just doing what's comfortable, honestly. I'll say this. This problem is more, I would say, computationally intense than what you would see on a final. I'm not an algebra guy on the final. That's not what I'm trying to get you all to do. I'm trying to get you all to do the structural design. So this was more intense than what you would get on the final. Sound good? Any questions? Okay. All right. If that's the case, then let's get into let's sort of finish out our final example for the semester, which is this one. So let's just get back into the swing of things and make sure everybody's clear on where we're at and where we're headed. So if you recall, we were discussing discretely braced beams as opposed to continuously braced beams. We know that unlike continuously braced beams, discretely braced beams want to buckle, okay? And their buckling capacity is a function of 2 things. Number 1, it's a function of how far apart your braces are, and 2, it's a function of your moment gradient. I mean, assuming you've got a shape and you know all the material properties and whatnot, you need to know how far apart your braces are and what your CB value is. So we're doing this example 24, where we're doing a fair amount of design, and the idea is that I want to give you all a lot of practice on determining whether or not a given section has adequate capacity. So my big goal is that you all understand how to navigate the beam charts. Now, we did, we did example, or case 1, where we had CB equals 1, and then we looked up a section, and it was pretty straightforward. And that's really what case 1 was all about. Case 1 was just trying to ensure that you all can navigate the beam charts. Case 2 was a little more involved. We had to compute CB and then adjust our moments accordingly. So let me go back to the example problem. So let's see. So here was the example problem. Let me go back one. There we go. Okay. So here's case one. Case one, we have a CB of 1, so we just calculated our MU, got 356 foot kips, solved, and we got a W16 by 67. Now for case two was a little more laborious because we had to go through and compute MA and MC. Now we knew MB and MMax were the 356 foot kips, but MA and MC we had to compute. Now we had to compute those using these expressions here. So is everybody comfortable with using these expressions over here on the right? Okay with that? Now we got a CB value, so it was like 1.295. So we divided that out. We got an MU over CB of about 275 and an LB of 20. And we got a trial shape of a W14 by 61. Was everybody okay with being able to locate that W14 by 61? Everybody okay with that? Okay. Now, I say that that is a trial shape for a very specific reason. In order to find this shape within the manual, we adjusted our moments by CB. As you know, whatever the heck CB is, it doesn't matter. Your capacity is cut off at MP. So it's very possible we could get, I guess the best way of describing it is a false positive. We could get a member that looks like it's good, but it's actually not. So whenever you have a CB that's not 1 or greater than 1, you need to go through and check your section. So this is where we left off last time. Let's go through and analyze this shape. So we're analyzing a W14 by 61. So what we need to do is we need to go to the ZX tables and look up some properties for a W14 by 61. Now, it is very possible that that's not a bold shape, and that's fine because the bold shapes are based solely off of ZX, but in the buckling realm, that might not, that might not match. So, let's start off. Has everybody been able to find the W14 by 61? Okay. Is it a bold section or not? No. Okay. Again, that's very possible. Okay. So, what page is everybody on so everybody's aware of this? 325. Okay, so you're on the fourth group down. Now, the first thing that we need in order to analyze this section is LP and LR. So what is LP and LR for this section going to be? Feet. And LR is, bless you. Now, for case 2, does anybody remember what L sub B is? "20 feet, right? So what does that mean? What zone are we in? Well, if there's a middle one, bless you, then there's a 1, 2, and a 3. Just so everybody's aware, when you're in the process of beam design and you go back and analyze, more often than not, and I would say just about every time, you should be in zone 2. Most beams that we design are going to be designed for inelastic buckling, or discretely braced beams, I should say. So everybody just be aware of that. Bless you. Okay. Now, does anybody remember what's the equation to compute the capacity of a beam in zone 2? We use that funky FCR equation. That's zone 3, right? To calculate the capacity for zone 2, we need 2 more parameters, right? What 2 parameters do we need? We need phi MP. Well, we're trying to compute phi MN. We need phi MP, and we need phi BF, our beam factor. So help me out. What is phi MP, and what is phi BF? Let's start off with the top one. 383 foot kips. And what's phi BF? Okay. Everybody okay on that? Now, I want to make an observation that might not make a whole lot of sense right now, but it will later. Okay, so phi MP is 383, right? What is our maximum moment, mu, for this section? So it was 356, right? mu is 356, right? So phi MP is bigger than that, right? I want you to just sort of keep that in the back of your head, okay? Now, while we're at it, before we do any other math, just keep that relationship in the back of your head. Now, what is Ix for this section? And are we okay with that value? Yes. Because that value is larger than our Ix min. So is everybody okay with that? I know it's been a while. But everybody good? Remember, what was our Ix min? 490 something, yeah. So, okay. All right. So in order to analyze this section, in order to determine phi mn, it is the minimum of the following quantities. So CB, phi MP, bless you, minus phi BF times LB minus LP, or phi MP. All right, so let's start plugging and chugging. So we have, what was C sub B again? 1.295. Phi MP is 383 foot kips minus 7.48 kips times 20 feet minus, what was it, 8.65 feet? And phi MP is 383. So what's that math come out to be? Now, while we're at it, I'm going to show y'all something. So, case 1, what do we have? A W16 by 67? Let's just sort of keep that in mind. 386.04. Second on that? Okay. So, CB amplified our capacity, but I don't care what CB did, our capacity is limited to that, right? Make sense? So, is that section valid? Is that a valid section? Well, the capacity is 383, right? So let me write that over here. I know it's been a while since we've looked at this. So phi mn is 383 foot kips, and mu is 356. So looking at that relationship, is that good? Yeah. So use a W14 by 61. So if we just start tracking things, so case 1 was a W16 by 67, case 2 was a W14 by 61, what happened? Beam got lighter. All we did was a little bit of extra math, and that beam got smaller. Now imagine that beam was used 800 times in a given building. See what I mean? Just a few extra calcs, and you're able to save some weight. Doesn't seem like a lot now, but, you know, down the line, yeah, that would matter. All right, everybody okay with this? Yes. What do you mean? No, I totally understand. What I'll say is this: there really isn't. I know what you're asking about. There really isn't. But what I will say is this: if you notice, each chunk usually tends to have only one, like W14 or one W12 or one W16. I'm not saying that's all the time, but usually. So you can usually skip from one chunk at a time and say, okay, there's my W14s. It doesn't always work like that, but it makes it a little easier, you know. Like I'm looking at a couple chunks below, and there's a W16 by 50 and a W16 by 45 in the same chunk. But there's also only one W18, only one W12, so you can sort of skip from there. That's a good question, and there's not really a better pattern than that. Everybody okay with this? Sound good? All right, now, so now let's do case 3. Okay, now let's start off with the C sub B. What is C sub B for case 3? 1. So C sub B equals 1, so therefore the, goodness, I've got away from me. Therefore the MU over CB is 356. So when we use our beam charts, that's the value we're going to look up. Sound good? Okay, now, what is LB? 10 feet? So watch this. This is important. So here was our beam before. We had this. Excuse me. We had this. And we had this. Right? And this was 10 feet, and this was 10 feet. This was WU. This was PU. All right. Everybody okay with that? Now, last time, all we had was a brace here and a brace here, right? Okay, so last time, what we had MA, MB, MC, and then M max happened to be right there, right? Now, we have a brace right there. So is that center point still MB? No. Now what we're going to have is MA, MB, MC, and M max. Everybody see that? Yes. For case 4. I'm making the point for later. No, I know what you're saying, but my point is later, I want you all to understand that we can't use, like when we do case 4, we can't use the C sub B value from before. We can't use that, what was it, 1.295? We can't use that from before because we have a different spacing configuration. We're going to have to go back to those moment expressions that we calculated before and do a little bit more work. But everybody okay with that? You are right. For this section, we don't. Okay? Everybody okay so far? Now, you are right. For this case, we only have a CB. We have a CB of 1, so we don't have to do any checking. We don't have to do any more math. All we need to do is go into the beam charts, find 356 on the moment axis, on the y-axis, find 10 feet on the x-axis. Remember, go up, and then go that way and find your first solid line. So let's see where we're at. I'll go along with you. Who's got one? A W18 by 55. Does anybody have a second on that one? Yeah. Okay, now what page, just so everybody, if you're not there yet, what page is everybody on? 124. So if you're not on page 3-124, go to 3-124. Find your 10-foot over here, your 356. Those tick marks are at 3-foot increments, or 3 kip-foot increments. There, I said kip-foot once. So they're at 3-foot kips. So you're going to be a little bit below that one below 360, so about like right there. And then you should be a little bit past the 21 by 48, so you're going to go up to the 18 by 55. Does anybody not see that? It is okay if you don't. Everybody good? Now, because C sub B equals 1, there's no more iteration. So whatever section that we picked, we're good. So I guess to be diligent, we might as well check our moment of inertia as well. But go ahead. I'd say it really doesn't matter. You can go either way. Really what you're trying to do is this. Let me show you. It'd be easier if I pulled up the image. Here we go. So you're finding that particular point, and I'm saying anything in the blue region is safe. Anything in the blue region would indicate a section that has a larger moment capacity and has a larger unbraced length. So let's say here's your point. Okay, now can you see that's a W14 by 61? You see that? Whether you go right and find the W14 by 61 or go up, it's still going to be the same line. I would argue doing like that. The reason why is because more than likely you're going to have the shortest distance. It's possible that on some of these charts, let me see your manual. It's possible that on some of these charts, and this can get a little frustrating, but you find your point and you're like right here, and you go like that, or if you go up, you have to go to the previous page, so you're having to like go to different pages to find your section. So I would just do your best to try and find the shortest distance to your nearest section without trying to turn the page. Sometimes you have to, and there's really no other way of getting around it. So does that answer your question? Yeah. It's possible but rare. It's possible but rare. Let me say this. What happens in case 4 might throw a new wrinkle into the mix. But we'll get to that here in a second. Just bear with me on that. Now, what was the moment of inertia of this section, the W18 by 55? Did anybody look that up? 890. So I'll put note IX is 890 inches to the 4th. So that's okay, right? Because remember, no matter what, we had to pick a section that was under 490. 490 what? 497. Okay. All right, now look at this. What happened? It got deeper, but it got lighter, you know. Now, why? Well, because we threw another brace in there. You know, throwing another brace in there means it's going to have increased buckling capacity. You're taking that unbraced length and you're making it shorter. It's a lot like columns. You take a column and you make it shorter, it gets stronger. Right? Same idea. Okay? Make sense? Any questions? All right. Case 4 is going to get interesting. All right? I'm lazy, so I'm going to redraw this. I'm going to copy this. Okay. I mean for that to happen. Okay. So all right. Now I'm lazy, so I want to reduce the amount of math that I have to do altogether. I'm not going to be able to get away from doing some. Okay? Now, would you agree that the moment diagram is probably going to look something about like this? Like it's going to have some roundedness to it, it's going to have a point to it, it's going to be something about like that. Would you agree with that? Now what is this top value right there? And what is that? We have computed that value already, and what is it? 356. So we'll say that this is the MU diagram in foot kips. All right, sound good? So would you agree that for this segment, bless you, would you agree that M max is 356 foot kips? Would you agree with that? Okay, all right. Another thing, let me go ahead and do this. So before we had MA, MB, MC, and M max because the entire beam was unbraced. Now each half of the beam is unbraced. So I'm proposing that the moments we need to compute are like this, you know, MA, MB, MC, M max. Is everybody okay with that? Now I'm lazy. Have we computed any of those values previously? MB. Before that was MA, right? Or MC, right? Everybody okay with that? So what did we get last time? What value did we get? Anybody have a value? 187. All right. Everybody okay with this? Now, just so everybody's aware of a couple things, our factored load was 0.72 kips per foot, and our point load factored was 64 kips, right? Everybody okay with that? And another thing, our function for the distributed load was Wx over 2 times L minus X, and our function for the point load was Px over 2. Make sense? So if I throw a coordinate system on here like before, this is X and this is Y. If I want to compute MA, what value do I plug in for X? MA. 2.5 feet. Does everybody see that? If I want to calculate MC, I plug in 7.5, right? I don't need to do MB because I already did that previously with 5 feet, and I don't need to do M max because that's 10 feet. Everybody okay with that? All right, so let's take care of MA, and then I'll let you all do MC on your own and tell me what you get. So MA is going to be 0.72 kips per foot times 2.5 feet over 2 times 20 feet minus 2.5 feet plus 64 kips times 2.5 feet over 2. All right. So what we got for MA? 95.75 foot kips. Do I have a second on that? All right. And MC is just going to be the same thing, but with 7.5 feet. So tell me what you get for that. $273.75. Do I have a second on that? That's just plugging and chugging. Don't really need to write the equation all over again, I don't think. Okay. All right. So our C sub B calculation is going to be 2.5 M max plus 3 MA plus 4 MB plus 3 MC, all under 12.5 M max. Now, before we plug and chug, it doesn't really matter for this problem, but I guess I ought to mention it. Everything that goes into C sub B is taken as an absolute value, right? Don't have to really worry about that with this problem. Everything's positive. So, sound good? So what do we get? It's 1.62. Do I have a second on that? Okay. All right. Now, before we start looking stuff up in the charts, I'm going to need some help with some things. All right? You're going to like this. So let's start off with this. What is MU over CB? 356 divided by 1.62. What do we get? 219 point what? Point, we'll just say 0.8. Because we're going to use this to look it up in the chart. So that's about as good as we can get. Now, what's LB? 10 feet. Okay, bless you. All right. Now, this is what we're going to do. All right. Everybody, we'll say from Tyler and Julius this way, I want you looking in the beam charts. Everybody from Kyle in this way, I want you looking in the ZX charts. So if you're Kyle in this way, go to the ZX table. And if you're at the beam charts, or if you're Tyler and Julius, go to the beam charts. You're going to like this. Now, let's be clear. What is our maximum moment? I'm going to put it on the board here. What's MU? All right, 356. Okay. Now, everybody over here, what's the first section that you found? Say it again. W16 by 40. Did everybody else over here get a W16 by 40? Okay. So let's do this. W16 by 40. Now, everybody that's from Kyle on over, I want you to tell me what is phi MP for a W16 by 40. Phi MP. 274 foot kips, right? Now, watch this. Should I do any math? Why? What's that? Yeah, I don't care what C sub B does. I don't care what the math does. Whatever the math is, the capacity is going to be limited to 274, and that's not enough, right? This is what I meant by a false positive, okay? You look up a section, it looks like it works, but then if you were to go through and do the math, The very best case scenario would be that your moment capacity is 274. Okay? That's not good enough. So for you folks that are in the beam charts, and the rest of you all, I want you to go through the beam charts as well because I want you all to see this. So everybody over here, go to the beam charts. What I want you to do is this. So everybody find the W16 by 40, and then what I want you to do is this. So you went like this. You found the W16 by 40. Find the next one. 14 by what? 14 by 43. Now, is everybody able to see that? Okay, now to reduce your all's turning back and forth, I'm going to be nice to you. I'm going to tell you that if you look up the phi and P for a W14 by 43, you get a phi and P of 261. So, do it again. What's the next section? Now, what is phi and P? Ooh. Now, is that a section worth doing the math on? Yeah, that's a section worth doing the math on. Possibly. So here's what I would put. I would put no good on this one, no good on this one. Maybe. We don't know. That's what the math is for, okay? Does that make sense? All right, does anybody have any questions on that? That's important. Didn't even, no point doing any of the math on those first two sections because I don't care what you do, you're going to be limited to 274 and 261. That's the point. Yes? Mm-hmm. Mm-hmm. Excuse me. No. Usually you're only going to get stronger capacity along the same depth if the section gets heavier. So the reason why the W21 is so substantially stronger than the other two, and they're all about the same weight, is because it's so much deeper. I mean, the W21 is about 21 inches deep. This is only about 14 inches deep. I mean, how do you get moment capacity? It's 4 times the distance. You want to get those flanges as far away from the middle as you can. That's why beams, if you look at beam sections, they're incredibly deep. Column sections are pretty square, so they're pretty compact. So, yeah. Does that make sense? Everybody else? Everybody okay with that? Okay, so the W21 by 44, that's a section worth analyzing. Does everybody have everything on this sheet? Can I move on? Okay. Okay. All right, so let's analyze. Let's get ahead of myself. A 21 by 44. So in order to do the analysis, we do the same thing as we did before. The first thing that we need to check is LP and LR. So what's LP and LR for this shape? So again, what zone are we in? Yeah, because LB is 10 feet. So we're in zone 2. All right, and again, in design mode, that will happen more often than not. Now, while we're at it, what is the, what's the moment of inertia? So that's just something to check at the very end just to make sure that you're good. That's the only deflection check we're doing on this entire problem, is that. A whole lot easier than concrete design, right? Deflections were a thing there. Okay, so We need two more values. We need a phi MP, which we already looked that up. That was 358. And we need a phi BF. What was phi BF? Or what is it for this section? 11.1? I have a different value. That's what I have. That's 16.8 kips. Is your sale? Yeah. Is yours not saying that? What? Oh, okay. Oh, yep. Okay. So, because we're in zone 2, our capacity is the minimum of either MP or that linear fit. That's C sub B times phi MP minus phi BF times the quantity LB minus LP brackets or phi MPX. Now again, your C sub B value is 1.62. We're not using that value from before because that C sub B from before represented a different bracing scenario. So it's just something to keep in mind. So 10 feet minus 4.45 feet, and then 358 foot kips. So it's the minimum of 358 and something. Say it again. We really don't need a decimal. So the capacity is 358 foot kips. So phi MN is 358 foot kips, and what's MU? 356. That is about as good as it gets. So look at this. Again, got lighter. All right, does that make sense? Okay, here's what I'm going to do. Shear doesn't really matter. You can look at the handout I gave you, but it really doesn't matter. And you can look at the numbers. I mean, I think we've done enough beam examples in this class to know that for beams in buildings, shear just doesn't really matter. I mean, we calculate a load of 20 kips, so we end up getting a capacity of 120 kips. So if you want, I'd be more than happy to post a video or do something on that, but there's really no point about talking about it in class. So with that, here's the deal. Friday, you all are turning in homework 9. I'm giving you the solution to homework 9. But that, ladies and gentlemen, is steel design. Friday, we will have our exam review, but I have no more topics left to teach you. So we will, with that, I'm going to call it, and I will see you folks in concrete here in a few minutes, but for the rest of you, we'll see you on Friday. Yes?
Did we ever talk about
We're still missing folks. What's that? Oh. Well then, I mean, you heard my rule. We got to have everybody here. Let's see. We're missing Maud. Are we missing anybody else? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17. I think he's the only one we're missing, so. No, we're not doing that. Everybody's got to be here. If we want to have this discussion, we'll have it. Let me say this. I think it's a good idea for there to be a buffer between the concrete exam and the steel exam. And this is coming from what you all have told me, that the classes tend to bleed together. Having a little bit of a buffer is probably a good idea. I'm more than happy to move the exam, but I've got to have everybody here to ensure that we're moving it to a date that works for everybody. It sounds to me like probably the most feasible date to do it is on Wednesday. See, this is why we got to have everybody here. So, I mean, I'm more than happy to move it. Doesn't bother me, but I'm not moving it, and then somebody down the line says it conflicts or whatnot. So we got to have everybody here. What's that? Well, we'll Friday. We got to have everybody here. Okay? Sound good? All right. We'll discuss that on Friday.